Bismillah ar-Rahman ar-Rahim. I again welcome you all in the lecture number 6 of Engineering Dynamics course. In this lecture, we will discuss the curvilinear motion in Cartesian coordinates. Curvilinear motion is the motion along a curved path. For example, a car is turning, anything which is moving in a circular path or in a curved surface. That is called curvilinear motion. But we are talking of the curvilinear motion lies only a single plane, like the motorcycle is turning, cycle is turning, or anything which is turning on a plane. If you see, this is the x coordinate and this is the y coordinate, and this is any point A at a radius r. Now it moves on the curved path, moving a distance of delta s, and move from point A to point A dash. This is the path of the particle, and now the new radius is r plus delta r. If we add them together, is r plus delta s or delta r, because this change in the point A and A dash are very close to each other. So that is delta r, and of course velocity along this curved path will be delta r by delta t. If you see the velocity at this point A, this is v, and velocity at A dash is v dash. It is tangent to that particular point. If we draw the two velocities together, this is and add them together, so v, this is v dash, and this is the change in velocity, because v plus dv will give you the new velocity. This change in velocity at a particular time is called acceleration, and that is the acceleration of a particle towards its center. That is also called centripetal acceleration. So this is the basic theory. I hope you understand. If any question, please put on the WhatsApp group. So the relationships, the instantaneous velocity, the velocity of a particle moving in a curved path in this case at a particular instant is called the instantaneous velocity. We say delta r by delta t, limit delta t approaches to 0. Of course, the instantaneous velocity will be as accurate as possible when the time interval is very small. And in simple words, we can also write v is equal to dr by dt, which is equal to r dot. Similarly, the instantaneous acceleration is limit delta t approaches to 0, delta v by delta t, or a is equal to v dot dv by dt. So these are the relationships that we will use when we are dealing with the curvilinear motion in a Cartesian coordinates, means in a plane. Okay, rectilinear coordinates. I'm talking of in a plane. So this is the x direction, this is the y direction. The unit vector in x direction is I, and the unit vector in y direction is j. There is any particle in the same way at A, particle at this position A have a radius r. So the velocity at this point will be, of course, tangent to that particular point, and it has two components, vx and vy. Similarly, the acceleration is towards the center of curvature, and therefore this is ax, this is ay, because centripetal acceleration is always towards the center, which basically is a force, the centripetal force, which tries to move the body in a curved path or in a circular path. So if I write the position here of r is xi plus yj, and if you take the derivative of this r, then you get the velocity of this particle in x and y coordinate, is x dot I plus y dot j. And similarly, the acceleration, if I take the derivative of this velocity, I get v dot r double dot x double dot I plus y dot j. Hence, if I need to find the value of r by knowing x and y, r is equal to under root of x square plus y square. Similarly, if I need to find the velocity, because velocity here is vxi plus vyj, so its velocity v is equal to vx square plus v square under root, according to the Pythagoras theorem. And the angle between the velocity, vertical velocity, and vx, so vx tangent theta is equal to vy by vx, you get the angle theta which v is making with the horizontal velocity. Similarly, the acceleration, which is in this case a centimeter acceleration or angular acceleration, is a square is equal to ax square plus y square. Similarly, ax square plus ay square ruled by using the Pythagoras theorem. We can also find the angle also here from the tangent theta is equal to, of course, ay by ax. So just write the position vector r, and then take the first derivative to give you the velocity, take the second derivative you get the acceleration, and then you can find the magnitude and the angles by using the same Pythagoras theorems and the tangent theta. Now, one of the very important application of the curvilinear motion is the projectile motion. Projectile motion is a motion in two dimensions, is a classic example of plane curvilinear motion. For example, if you throw a ball, or you throw a missile, or if you throw a rocket at a certain angle of theta with some initial velocity is v naught. So this velocity will have now two components. One component is along the x-axis and other component is along the y-axis. So Vx naught initially is v naught cos of theta, and Vy naught is basically v naught sine of theta. As you move along this, I'm talking of, we give the projectile initial velocity and there is no power during the whole flight, only the initial velocity is there. So if you move from point A to point B, of course, the value of g is downward, and of course, at any instant we need to find the velocity, we get Vx and Vy. And then we come downward, of course, Vx is in this direction, in Vy is this direction, in the downward direction, of course, and if you move upward direction, the vertical component is decreasing and horizontal component it remains same, because in the horizontal direction there is no force, there is no deceleration. But in the case of vertical motion, there is a negative acceleration, which is minus 9.81 acceleration to gravity meter per second square, right? So it is decreasing, and then it at a maximum point it becomes 0, at maximum height it becomes 0, and then it is going to be increased. So the horizontal component remains same, which is Vx, and which is v naught cos of theta. There is no force in this direction, so this component remains same, but the vertical component initially decreases and then finally increases, and resultant you can find out at any point by Vx square plus Vy square under root. I've shown again these terms was mostly used. This is v naught of x, this is v naught of y, initial velocity component of x, and the x component of the velocity at any instant is remain same. The vertical component is decreasing as you move in the upward direction. At the maximum height, this is h, which the projectile will achieve with a certain angle and a certain initial velocity, and of course Vx is equal to v naught x is constant, and the vertical component velocity is 0. When you move in the downward direction, now the acceleration is in the direction of the movement, therefore the vertical component is increasing, but horizontal component have no force, therefore it is constant, and it is increasing, and then at the end it reaches the final point. And at this final point, if I ignore the resistances, air resistance and any other, then this y component is same as the initial y component, only the direction is reversed. This the point from where we hit the missile or a ball or throw a ball, and again when they hit back to the ground, that is called the horizontal range of the projectile. So when you're solving the problems of a projectile motion, you will take care of horizontal motion separately and vertical motion separately. In this, the projectile motion that I have discussed now, that we have given the initial force, initial velocity to a projectile, and it's now moved freely. But if during the flight there is some force, then of course we may have an acceleration in x direction, and we may have acceleration in the y direction. Now let's move the next topic is the time for maximum height and time for total flight of a project when it's of a projectile when it is given an initial velocity of v naught or v. Time for maximum height. So as we are talking of the height, and height is in the vertical direction, for this we consider the motion in the vertical direction. Of course, there is no force in the x direction, so ax is equal to 0 and ay is equal to minus g. The initial velocity vertical velocity component is basically it is v naught sine of theta, and final velocity is 0 when it is at the maximum height. You know that I have shown you earlier here that Vy is 0 at maximum height, right? And then A is equal to minus G. If I use the same Newton equation of motion but only for vertical direction, Vf is equal to Vi minus Gt. I'm talking of the initial and final velocity in the vertical direction. So Vf is 0, Vi is V naught sine of theta minus Gt, and we get the time, which is V naught sine theta upon G. This is the time taken by the projectile to reach a maximum height. Time for total flight is, of course, time going from point A, from this point to maximum height, and from maximum height to final point is same. So the time for total flight is 2V naught sine theta upon G. So time for maximum height is V naught sine theta upon G. Time for total flight, which is used for horizontal range, is 2V naught sine theta upon G. Next thing, I am trying to find out the horizontal range. Horizontal range, of course, because there is no force in the horizontal direction, so it is simple. S is equal to Vd. So we say here, mostly we show R V naught cos of t. T, capital T, is basically time taken for total flight, which is 2 times of the time taken to reach the maximum height. I have shown you in the previous slide. So it's V naught cos of theta. It is 2V naught sine theta upon G, right? So this becomes, when you multiply, we get V naught square 2 sine theta cos theta upon G, and 2 sine theta cos theta is called sine 2 of 2 theta. So now the next question is, when the horizontal range is maximum, when we throw a projectile, a missile, a rocket, a ball, anything at some initial velocity V naught. It is maximum when V naught and G is constants, then sine 2 theta is equal to 1, because the value of sine is maximum, that is 1. So sine 2 theta is equal to 1, and 2 theta is equal to sine inverse of 1, which is goes to be 2 theta is equal to 90 degree and theta is equal to 45 degree. Hence, if we throw a missile or a projectile or a shell at certain velocity, then you get the maximum horizontal range at an angle of 45 degree. For further elaboration for your knowledge, sometimes we try to find, of course, we also need to find the maximum height. What is the maximum height the projectile will reach? When I'm talking of the maximum height, I will take the motion in the vertical direction. So in the vertical direction, initial velocity is V naught sine t, and time taken is V naught sine theta upon G. So if we use the formula, H is equal to VIT minus half GT square, Newton's second equation of motion, because G is constant. So V naught sine theta, time is V naught sine theta upon G minus half G, and this is T square. So we get V naught square by G sine square theta minus V naught squared by 2G sine square theta. Simplify, you get V naught squared 2G sine square 2 theta. This is the maximum height a projectile will reach if you throw a projectile at a certain initial velocity V and angle theta. Now let's, if I try to find the trajectory, what the path followed by the projectile means, this is the path, how this path is to be obtained. So if I need to find this one, of course, we can plot, we can find out the projectile trajectory. So for this case, for example, we know that y is equal to v naught sine theta t, which is basically vit minus half gt square. We know that x is equal to v naught cos of theta times t. And what is t? T is equal to x over v naught cos of t. We take that time, why are we taking the time this only t? Because it's a time taken to reach to maximum height. So I put the value of t in this equation in terms of x, v naught sine theta, x over v naught cos theta minus half g, t is x over v naught square cos theta whole square. This v naught cancel out, sine theta upon cos theta becomes tangent theta, so it becomes x tangent theta minus this is g sec, of course this 1 by cos square sec square theta 2v naught square x square theta. The final relationship for the projectile trajectory, if you know the angle theta and the v naught, and of course g is constant, we can find a relationship between y and x. Y is equal to x tan theta minus g by 2v naught square sec square theta x square theta. If you know the value of x, angle theta and the v naught, you can find the y, and if you know the y and you know the angle theta and v naught, you can find any position of a y. So if I set a certain angle and give you the value of v naught, you just vary the value of x. You can plot the trajectory of a projectile, which is look like this, right? So this is the trajectory equation, which is mostly used when we solve the problems. Now the next important parameters for the projectile motion is angle at which height and horizontal ranges are equal. You know that the horizontal range is v naught square by g sine 2 theta, and maximum height is v naught square by 2g sine square theta. We need to find when r and h are equal. We compare these two equations. Of course, v naught squared by 2g and v naught square by 2g cancel out. 1 sine theta, this square is cancel out. We get 2 cos theta is equal to sine theta. Our tangent theta is equal to 2, or theta is equal to 63.4 degree. It means at a certain initial velocity of v naught, if you hit a projectile at 63.4 degree, then the height and the horizontal range are equal. If height is, for example, 5 meters, then of course range is also of 5 meters. This is a special angle which is mostly to be taken into account, where the both of them are equal. Okay, so this is the important things which I have derived. That is the time taken for maximum height, time taken for total flight, the horizontal range, the maximum height, the trajectory of the projectile, and the angle at which both horizontal and vertical distances are equal to 63.4 degree. So we have the basic knowledge. So now we try to solve these sample problems 2-5. The curvilinear motion of a particle is defined by Vx is equal to 50 minus 6t, and y is equal to 100 minus 4t square, where Vx is in meter per second, y is in meters, and t is in seconds. It is also known that at x is equal to 0 and t is equal to 0, it says that plot the path of the projectile and determine its velocity and acceleration when the position y is equal to 0 is reached. So we have given the velocity Vx. For x we have given the velocity Vx. So from this Vx, by integrating, we can find the x in terms of t. So I can say dx is 50 minus 60t dt from 0 to x and 0 to t. When I integrate and applying the limits, we get 5t minus 8t square in meters of x. And for the acceleration, we take the derivative. So it becomes ax is equal to v dot x, which is equal to minus 16 meter per second square. Y is already given to you as a function of time. So y is equal to 100 minus 4t square. We know the value of x. We know the value of y. We only need to find the time t when y is equal to 0. That we find out later on. First of all, I'm trying to find the velocity in the y direction. Taking the first derivative becomes minus 8t meter per second, and take the second derivative becomes minus 8 meter per second square. So we knew this is the previous knowledge of the rectilinear motion is to be used, right? So now we have a x relationship, y relationship, the x velocity, acceleration in x, velocity in y, and velocity and acceleration in y direction. Now we can plot the trajectory between y and x at different values of at different time intervals. So let's one of the question in the problem that we have to find out the time at which velocity is y is equal to 0. So I take the y equation and put it equal to 0. So 4t minus 100 is equal to 0, t square is equal to 25, and t is equal to plus minus 5, which is 5 seconds. At 5 seconds, Vx, I put the value of t in Vx, is 50 minus 16 into 5, so minus 30 meter per second. Vy is equal to minus 8 into 5, minus 40 meter per second. And it means V is equal to minus 30i minus 40j. And if you need to find a magnitude, it is 30 square plus 40 square into 50 meter per second. And similarly, acceleration is minus 16i minus 8j. right? That we have find out the acceleration in the previous slide. So similarly, x square and y square, we get the value of the acceleration. The graphical representation of velocity and acceleration is shown here. Let's see. This is the path with the orange line, path followed by the body, and this is the component of the velocity vx, of course in the negative x direction, and of course y is also negative x direction. This is the resultant velocity 50, and if we need to find the angle, we can find out tangent inverse 40 upon 30. Of course, it is the fourth quadrant, and you see it is in the fourth quadrant. Sorry, it is the third quadrant. Both of them negative. The third quadrant. Similarly, acceleration minus 16 meter per second square in the negative x direction, and similarly y in the negative x direction. Right. So these are the way how can show that this is the way how the acceleration is represented, and this. Now the next job is to plot the trajectory. I'm plotting the trajectory for from 0 to 5 because after 5 seconds the position y becomes 0. So very simple. I write this very small code which I have written already in the previous lectures, which I clear all the variables of this name with from the RAM, clear screen CLC, clear the screen. I define a value of the t from 0 with the increment of 0.1 and finally with the value of 5. Initial value, final value is 5, and this is the increment. You can increase the increment, you can decrease the increment with 0.1. Of course, you see the graph is very smooth. So x is equal to 50t minus 8t square. Please, we are taking the square of the individual variable. It should be dot hat. Similarly, 100 minus 40 square, and we give the command plot x comma y, and x label show you this is the label x in meters, and y label is y in meters, and I grid command is the new command used in this code I to show you the grid that is this grid is squares are coming. This is the grid which and this will help you to read, and you see this same graph is obtained as shown in your book. It is a parabola, and this is the projectile trajectory which is given in this case. So this has been plotted like this, right? That at a 0, so at t is equal to 5 seconds, y becomes 0, and the displacement is x is of course 0, and here at this this is the at y is equal to 0 at x is 50, right? And when x is equal to 0, y is 100 meters. This is the way how you can find the position at different intervals of time between x and y. I hope this question is clear to you. Okay, the next sample problem is 2-6. Sample problem 2-6 says a team of engineering students design a medium-sized catapult which launches 8-pound steel sphere. The launch velocity is V0 is 80 feet per second. The launch angle is 35 degrees above the horizontal, and the launch position is 6 feet. This is a little bit high, is 6 feet above the ground level. The students use an athletic field with an adjoining slope topped by an 8 feet. This is the 8 feet. This one is 8 feet fence as shown. Determine the xy coordinate of the point of first impact, where this when you hit up these steel balls, where they hit first time. Then the time duration tf for the flight, how much time it will take to reach that particular point is final. The maximum height h above the horizontal field obtained by the ball. What is the maximum height it will achieve from this horizontal, right? This horizontal, please. This is 6 feet should be added. The velocity expressed with which the projectile strikes the ground. Okay, with which velocity it will strike the ground, the x component and the y component of the velocity. So in this question we are given V0 is 80 feet per second. This, and of course the weight of the balls are 8 pounds, and theta is equal to 35 degrees. If I take the in the horizontal direction, the x is equal to x0 plus Vx of t. x is equal to vt, because here if there is initial distance, then we will add. So here x is basically 100 plus 30. This is initial hit, right? So this is 130, initial is 0, so this is 80 cos of 35t. This is the time it take to reach that particular, to hit that particular point first time. Now the vertical distance, y is equal to y naught plus vit, with y of naught t minus half gt square. This is y. Initial y distance is here, which is 6 feet, right? Plus 80 sine of 30, 1.984 minus half gt square. G is basically 2.2 because it is an FPS system, and the time we have found out to reach that particular point is this much, right? So by solving, we get y is equal to 33.6 feet. This is the height at this point, is 33.6 feet. It is clearly shown because this is 20 plus 26. This is yes, 26 feet, 28 feet, and this is 33 feet. It is clearly past the particular feet, right? It is crosses this fence because this is 28 feet and this height is 33 feet. Now let's put y is equal to 20 feet. Why I'm putting y is equal to 20 feet? Because we need to find, okay, this is 20 at this. If we hit this point, then what are the velocity? That is the requirement. So y is equal to y naught vit minus half gt square, because I need to find the time of the flight when it reaches here, at this point, and this is 20 feet, right? This is the next question, next requirement of this question. So this is 2680 sine of 30 tf, and I got the quadratic equation in the final time, the time for total flight when hit the at the bottom of that particular fence, which is tf square minus this much. So the two times, 2.5 second and 0.35 second. Of course, this is not possible. So it's 2.5 seconds. So what is x? X is equal to x naught vx of t. The x is equal to 0, 80 cos of t. So we find the point, it is 164. These are the coordinates 164 and 20. 164 here, when you hit this here, right? If there is no fence, this is 164 is here almost, an x, and then there's a y is basically 20 feet where this first hit the ground. Now maximum height simple, vy square is equal to vy naught square minus 2g y minus y naught. So 2as is equal to minus vf square. This is 2gs y minus y naught if there is initial distance. Yes. So vy is 0 maximum height, and the initial velocity is of course 80 sine of 35 degree, and this 2 times of g 32.2. The final height of this is h minus 6. Again, h is equal to 38.7 feet. The maximum height it will achieve by this velocity of 80 feet per second, right? So this is the maximum height which is achieved, and the final thing is the x. So what is the x it will achieve? Vx is equal to v naught cos of 35 is 65.5. Now we know that the final velocity vy is equal to v naught y minus g of t. That is 80, 35 minus 32.2. We get minus 34.7 feet per second square. Because I need to find what are the velocities at TF when it hit the ground, right? The x component and the y component. The x component is simple, v naught cos of t remains same, 68.5. The vertical component vf is vi plus 80. So this is minus 34.7. So it is 65.5 I minus 34.7 j. Or the magnitude is 74.12. So its x component is positive and y component is negative when it hits the ground, right? Its x component positive and y component is of course downward, which is very clear, and that is positive. And this is the velocity in the vector notation and in the magnitude when it hits the ground, right? So this is the end of this lecture. I have solved. I'll give you the basic concepts of a curvilinear motion and electric coordinates, and of course give the projectile motion. We have find out its time for maximum height, maximum flight, means horizontal range, maximum height and trajectory, and angles at which both horizontal and vertical heights are same, and solve the two sample problems. In the next lecture, inshallah, I will talk of the problems regarding these 3 to 4 to 5 problems for you, and this topic will be ended. Then we go to the entry corners. Students, you should go through these lectures and do yourself. Of course, it is good for you when you come to university. Then it becomes easy for you to cope up these lectures. Thank you very much.